Okay, so today is the last lecture in this semester. It's about chapter 16, capacitors, quick revision. Uh, a parallel plate capacitor is an electric device that has two plates parallel to each other. Each has an area A, and they're separated by a distance D. When they are connected to the battery, there will be charging of the capacitor, and the charging will stop when the charge on the positive capacitor is equal to plus Q, and the charge on the negative capacitor is minus Q. Okay. An important aspect of a capacitor is the capacitance, and it's equal to epsilon 0 A over D, where epsilon 0 is a constant. It's 8.85 times 10 power minus 12 in SI units. The area A is the area of the one plate, and D is the distance between them. And the unit for capacitance is farad. Usually, capacitors have very tiny capacitance, so the unit would be microfarad, where micro is 10 power minus 6. Then we can talk about the charge on the positive plate, which is the Q. Q is C, which is the capacitance that we have just calculated, times V, which is the voltage across the battery. And because now we have positive on one plate, negative on the other plate, there will be a stream of electric field from the positive to the negative. Okay, so there will be an electric field. Yeah, remember when there is a charge, positive charge, it will create around it an electric field which is outward, and when there is a negative charge, it will create an electric field inward. So the electric field will be going from the positive to the negative, and this is equal to the voltage across the battery divided by D, which is the distance between the two plates. 2 units for E. One of them is voltage per meter, and the other one is the normal one that we know, which is a Newton per Coulomb. Okay. Then capacitors are used to store energy. So the energy stored in a capacitor, in order to calculate it, it's U. We refer to it by U to differentiate it from E, which is the electric field. And it's half QV. Okay. Now, if instead of Q, I put CV, I get half CV squared. And if instead of V, I put Q over C, I get half Q squared over C. So all these are equations for the energy. So these 4 equations are to be memorized for a parallel plate capacitor across a battery. The 4 equations right here. Now, usually people tend to combine capacitors in order to get a certain amount of capacitance. And the two simple ways of combining these capacitors is in parallel, where the C equivalent will be the summation of these 3 capacitors, okay? The voltage across each capacitor will be exactly the voltage across the battery because these are in parallel. And the Q across the total circuit, the Q will be equal to Q1, which is across C1 plus Q2 plus Q3. Okay, so Q total is Q1 plus Q2 plus Q3. And if I want to get the Q across one particular capacitor, I will have to use the formula Q across that capacitor divided by Q total, which is a Q across the whole thing, is equal to this capacitor, the capacitance of this capacitor divided by the C equivalent. Okay, so this is very important formula. You need to memorize it in case I have a parallel combination. Now, if I have a series combination, in order to get the C equivalent, I have to use the formula 1 over C equivalent is equal 1 over C1 plus 1 over C2 plus 1 over C3. The voltage V across the battery will be V1 plus V2 plus V3, okay? And the Q total across the battery is exactly Q1, is exactly Q2, is exactly Q3, okay? So these need to be memorized. Actually, I've shown you in the lectures how to do the derivation of the equivalent capacitance, but you are not responsible for that. You can just memorize it. In series, you have to do the reciprocal of the capacitors, and then you add them and you divide by that. And in parallel, you just add them, okay? Now, let's do one last exercise. This is page 57 number 8. So using the adjacent figure, find the equivalent capacitance of the whole thing. Okay, so let's give these things names. So this, let's call it C1, C2, C3, and C4. Okay, one can directly see that C1 and C2 are in parallel, right? And C3 and C4 are in parallel. So we start. C1 and C2 are in parallel, implies C12 is equal C1 plus C2. C1 is 1 microfarad plus 5 microfarad. So this will give me 6 microfarad, or 6 minus 6 farad. And then I can see that C3 and C4 are in parallel, implies C34 is also the addition. So this will give me 8 plus 4, 12 e to the minus 6 farad. Okay, then C12 plus and C34, if you can see this, you can see this here. In this drawing. So after I get C12 and C34, one can see that these two are in series. So back here, C12 and C34 are in series. So one over C equivalent for the whole circuit is equal to 1 over C12 plus 1 over C34. I plug the numbers. This is 6 e to the minus 6. And this is 12 e to the minus 6. And I will get the answer for the whole circuit to be 4. So I will get C equivalent to be 4 e to the minus 6. Okay. Okay. Now find the charge on each capacitor. So let's remove this and this. Now, what do we have? We have, we agreed that C12 and C34 are in series. So we have Q across the whole circuit is equal to Q12 is equal to Q34, right? Because they are in series. So C12 is equal to C34 is equal to Q total. So we start by that. So I have Q12 equal Q34 equal Q total. And what's the Q total? Q total is C total, which we call it T equivalent, times the voltage across the battery. So that's 4 e to the minus 6, C equivalent, times 24, and this gives me 9.6 e to the minus 5 coulomb. So why did we apply this? Because C12 and C34 are in series with the battery. Okay, so this is why we could use this. Okay, so we have Q12 and we have Q34. Now, C1 and C2 are in parallel, implies Q1 over Q12 is equal C1 over C12. So here we are applying this formula. When we have parallel combination, we have the charge on one capacitor divided by the Q across all the capacitors is equal C across the capacitor across divided by the C equivalent. So I use that. So I have Q1 and C1 and C2 are in parallel, implies Q1 divided by Q12 is equal to C1 divided by C12. So I get Q1 is equal C1 times Q12 divided by C12. And numbers, C1 is 1 microfarad times Q12 is 9.6 to the minus 5 divided by the equivalence of C12, C1 and C2, which is 6 to the minus 6. And I get this number to be 1.6 e to the minus 5 Coulomb. I do the same for Q2. I will get Q2 equals C2 times Q12 divided by C12, and this will be 5 e to the minus 6 times 9.6 e to the minus 5 divided by 6 e to the minus 6, and this would give me 8 e to the minus 5. Okay, similarly for C3 and C4. C3 and C4 are in parallel. So I do exactly the same thing. I will get Q3 equal to C3 times, or let me put it first. So Q3 divided by Q34 is C3 divided by C34, and this will give me Q3 is equal C3 times Q34 divided by C34, and if I plug the numbers, 8 e to the minus 6 times Q34, which is the same as Q12, the same as Q total, and that's 9.6 e to the minus 5 divided by C34, which is 12 e to the minus 6. 8 plus 4, 12 e to the minus 6. This will give me 6.4 e to the minus 5. And similarly, Q4 is C4 times Q34 divided by C34, and this is 4 e to the minus 6 times 9.6 e to the minus 5 divided by 12 e to the minus 6, and the answer is 3.2 e to the minus 5. Okay, part C. How much energy is stored in the 5 microfarad capacitor? So I want Q2, which is energy cross capacitor. Okay. So what's the formula? U2 is equal half Q2 V2, or 0.5 Q2 times V2. I have Q2, I have just calculated it, it's here, but I don't have V2. So let me use another formula. Instead of V2, I will use, so this will be Q2 times, instead of V2, I will use Q2 divided by C2, okay? Which means this will be square divided by C2. So this will be 0.5 times Q2, which is 8 e to the minus 5 square divided by C2, which is 5 e to the minus 6. And this is equal 6.4 e to the minus 4. Okay. So that's it about capacitors, and that's it about chapter 16. Tomorrow we will have, I'm gonna upload this on Google Classroom, and tomorrow we will just have a live session where we will work more on chapter 16 and solve one exercise on combination of capacitors, because this is very important. And that's it for now. Bye-bye.